Chapter 4, Section 23, Outlier Detection by Shrinkage Covariance Matrix, Part 2. This section covers Python coding for outlier detection by shrinkage covariance matrix and discuss the comparison between MCD and shrinkage covariance matrix. Now, let's detect outliers using the shrinkage covariance matrix. First, import Ledoit-Wolf from sklearn.covariance. We use it to run Ledoit-Wolf shrinkage. Then, to simplify the problem, we create a dataset consisting of only two variables and name it x. Now, let's execute the outlier detection. First, initialize Ledoit-Wolf as LW to run Ledoit-Wolf shrinkage. Then, fit the dataset x to this LW. Next, compute the mean of each variable. To calculate the mean values of each variable, set axis equals 0 to compute the mean along the columns. Use 2_numpy to convert the data frame to a numpy array. This operation makes numerical computation easier. Next, use covariance_score to retrieve the shrinkage covariance matrix. Since the shrinkage covariance matrix has already been calculated when we feed the Ledoit-Wolf to the data, we simply retrieve it here. Then, use numpy's linear algebra module to compute the inverse of the shrinkage covariance matrix. Next, let's define a function to calculate the Mahalanobis distance for each data point using the shrinkage covariance matrix. The function is named shrinkage_Mahalanobis and is set to include three arguments, x, mean, and imp_cov. The first argument, x, is the data point converted into a numpy array. The second argument, mean, is the mean vector of the entire dataset, containing the mean values for each variable. The third argument, imp_cov, is the inverse of the shrinkage covariance matrix. In the second line of the function, delta calculates the difference between the data point and the dataset's mean. This results in the deviation vector. The next line applies the formula of the Mahalanobis distance. Let's use this function to calculate the Mahalanobis distance. The apply method of pandas is used to apply the function to each row in the data frame x, that is, each data point in x. The parameter axis equals 1 specifies that the function is applied row-wise. In the parentheses, lambda row defines an anonymous function that takes each row as input. Row_numpy converts a row from a pandas series to a numpy array, making numerical computations easier. As a result, the Mahalanobis distances for all data points are stored in a pandas series object. Next, set the threshold value. The chi2ppf function calculates the percent point function of the chi-square distribution. Here, based on the chi-square distribution with degree of freedom, we calculate the threshold corresponding to a confidence level of 97.5%. The threshold is stored as the variable named threshold. This threshold defines the boundary at which the Mahalanobis distance is considered an outlier. Data points with the Mahalanobis distance exceeding this threshold are identified as outliers. Next, we determine whether each data point's Mahalanobis distance exceeds the threshold. The results of this evaluation are stored in a variable LW outliers as a Boolean array, where data points exceeding the threshold are recorded as true and others as false. Finally, We store the Mahalanobis distances calculated using the Shrinkage Covariance matrix and the outlier detection results in the data frame df. This data frame df was used in the previous section, where it stored the Mahalanobis distances and outlier detection results calculated using MCD. By adding the results from this section to df, we can easily compare the results of the two methods, MCD and the Shrinkage Covariance matrix. Now, let's display the results using scatter plots. Let's compare the results from the usual Mahalanobis distance, MCD, and a Shrinkage Covariance matrix by lining them up horizontally. The results are shown in these scatter plots. The orange dots are outliers. The orange dots exist only in the case of MCD. The method using the Shrinkage Covariance matrix did not detect any outliers. In the present results, MCD detected some outliers, but the Shrinkage Covariance matrix did not detect any outliers. Whether MCD or Shrinkage Covariance matrix is more likely to detect outliers depends on the nature of the dataset, the type of outliers, and the characteristics of the distribution. However, in general, MCD tends to detect more outliers for the following reasons. MCD selects a subset of the dataset that is less susceptible to outliers and estimates the covariance matrix and mean based on that subset. Because designed with the consideration of outliers, MCD works effectively even when the dataset contains many outliers. If outliers have distinctly different distribution, MCD is relatively sensitive to detecting them. However, MCD might miss outliers if the distribution of outliers is very close to the distribution of normal data points. The Shrinkage Covariance matrix applies shrinkage intensity to the sample covariance matrix to stabilize the estimates by suppressing noise. Since the Shrinkage Covariance matrix is estimated considering all data, it is susceptible to outliers. Thus, compared to MCD, the Shrinkage Covariance matrix is more likely to miss outliers. Therefore, generally speaking, MCD is more likely to detect outliers, but it depends on how extreme the outliers are and the nature of the data. Accordingly, it is advisable to conduct comparative experiments with actual data to evaluate which is more suitable for the analysis we are addressing. Thank you for watching. If you have any questions, feel free to ask in the comments. Your feedback is always appreciated.